welcome everyone. Thanks again for coming. And welcome to the final presentation for the FTC workshops. This one on control award and programming. So like always, it's a pretty small group, so feel free to unmute yourselves if you have a question. Otherwise, you can put it in the chat box and I'll relay it on to the two presenters today. And yeah, with that, I'll pass it off to Toya and then Ben to get us started.
Yeah, hi, I'm Toya. I'm the team captain of FTC, team 16660 Cybering, and I'm also a member of the programming team and FRC team 568, the Nerds of the North. It'll be my third year participating in FIRST. And for FRC, I also was responsible for programming a mathematics video game and a telepresence robot for the Nerds of the North.
Ben.
Hi, I'm Ben McLecky from HUNA, and I've been coaching various teams for a while. Yeah, it's a lot of fun. Anyway.
Cool. Well, with that, I think I'll pass it off to Ben to do the screen sharing and kick off the presentation.
Did you say me?
Yeah, are you the one presenting first?
Toya, I'm going to do the blocks programming. So Toya's going to do talk about the control award, I believe was our email correspondence. Is that correct?
Beginning part, I would do the beginning part. So I would just quickly screen share over here.
Yep.
Wait a little bit. Okay, so hopefully the screen sharing works right now. Okay, cool. So, so why should even like people care about having like, you know, better programming practices or like, you know, choosing the right variable names? Don't call any variables A or B or something like that nobody can understand. Well, people should understand that coding is like a collaborative thing and not just an individual thing, because even if you know what variable A means or what variable B means, you know, your other team members won't understand what that means. Or even you in the future, you'll just maybe you want to reference your code that you wrote, and then you're looking at it again, and all you see is like random stuff, all gibberish, and you wouldn't understand what you wrote yourself, and you don't want that. So that's why better programming practice is really important. I would say you should also, other than use good variable names, you should also put comments where you think your code would be confusing. And then so that even other people can understand what your code does. And as my rule of thumb, better programming practices reduce like redundancy. So if you're like copying, pasting a chunk of code multiple times, then there's probably like a better way to do it or a smarter way to do it. Either whether that's like using functions or whether that's using loops, you should probably like also kind of think, what might be like a smarter way to present this code and maybe even and perform the same thing with better code. There we go. So this is a quick thing that I do with code organization. So here's kind of what my team's team code looks like. So there's different packages. So this one's the one that everybody has. And then I have a hardware package that includes different types of drives, such as the main one we use, our differential drive, that's like arcade drive and tank drive. And then you also have the holonomic drive. So that's like the 45 degrees omnidirectional one, or whether that's a mecanum wheel. This is the one we use. And then I also have the gyro included in this hardware file because that's something that we use every single year. And then when you go after that, these are some more specific robots, like these are just names. Terrence, that was our name of a robot. Uncle Drew was last year's robot for us. So then we have a autonomous package over here, and then put every single autonomous programs in here. You can probably even do like a better way of organizing what's inside here. And then the hardware over here is, I have the hardware, each hardware separated, not all in one file, because that kind of confuses things and usually also makes it really, makes one really, really big file, which is not really good. And it's really usually confusing. So I separate it into multiple hardware files with the drive, the grabber, the scoop, the sensors. And then I have one teleop file that can be run in driver station. And so for programmers in FTC, there's this question of whether you should use or stay, I guess, in on-bot Java, which is what most people use, I would say. And then there's also blocks, which is the simplified version where you can drag blocks, which I personally have never used. Maybe Ben can elaborate on that one. Versus Android Studio, which is a software that you have to download to program your robot. So for each of these, there are different pros and cons. And I would say the biggest pro for the on-bot Java, and most likely blocks, would be that it's really, there's not much setup to do. It's all browser-based. There's no installation required or anything like that. So all you have to do is type in the IP address, connect to the Wi-Fi, and then type in the IP and you're in the URL, and you're done. You're there. You're already there. The build time is also really quick. When you just press build, instantly, it's basically the code is deployed to the robot. So that's one plus for the on-bot Java. And it's really easy to program wireless. And some cons, though, is that there is no thing called version control, which is basically just, it allows for bringing back old code, so old revisions of code. So when you think that you messed up some piece of code and then you can bring up old versions, you can't do that in on-bot Java. So that's one minus for that. And then on-bot Java is also what I call a dumb IDE, because you can't do much customization and it's not really a great user experience. It doesn't allow you to autocomplete or anything like that. It doesn't tell you what you messed up in the code. It only tells you the line number or something like that, and then be like, hey, you messed up. Well, I guess you have to fix it. So it's not really a great user experience. And then for Android Studio, which is what our team uses, it's definitely much more powerful than on-bot Java. And you can basically do anything that's allowed in FTC. And it's also what I call a smart IDE, contrary to the on-bot Java. So you can basically, it tells you what's wrong with your code, and it also it's like customizable IDE. You can have like fonts and whatnot if you care about that. You can also, there's also autocomplete. It also tells you the parameter values, what they mean. It's a much better user experience than on-bot Java. And it also allows for version control. So when you mess it up, you can also revive the older version of your code. So that always helps. That's definitely the biggest deal breaker for some people would be that it doesn't run on like the low capacity, or it definitely struggles to run on low capacity computers like Chromebooks and stuff like that. So that is definitely not good. And also it's really a pain to set it up, especially in this online format. So we've tried in my team, I've tried to teach how they can download Android Studio and set it up. It's really, really a pain to set it up. It takes forever. It's even more setup to do, like wireless connecting and everything. So I would highly recommend that you use this if you are really experienced with programming or just using computers in general already. Ben, is there anything that you would like to add for blocks as well?
No, you did a great job. I would just say that pretty much everything you said, there's an equivalent answer for blocks. So I'll give a couple of specifics on that later when I do the blocks 101. Yeah, okay. It was good.
And then we can go on to like what is the control award in the first place. So the control award is an award that is awarded or that is given to the team that uses like the most innovative and the best sensor uses in different aspects of programming, and how that kind of adds up to the driver experience, and also how that can create a really reliable and functional robot. So it really just connects the code to the robot, how well you can really control. That's why it's called the control award. How well you can control the robot, and how you can facilitate driver control with programming. And this year, the control award was ranked higher than the motivate award. Prior years, the control award was below the motivate award. So that's one reason why you should also probably aim for the control award. And here's like the submission form that you have to fill out to be eligible for the control award. So you have to just fill out your team number, team name, stuff like that. And then for remote competitions, you also have to send them a video link, so a video of your robot, working robot, and how it demonstrates all the different parts of like autonomous. It doesn't have to be for every single autonomous, but it just needs to reflect good programming. Well, I guess not good, but your different sensor uses and your programming. So you have to list your autonomous objectives, what you can do, so, and then your sensors used, what algorithms you have, how it can enhance drivers' experience, and you have to reference engineering portfolio, which is also why you need a good portfolio as well. And then you have to like draw what your robot can do in autonomous. So this is kind of a full control award submission form. And I would like to talk about what we can do this year as well. So each year there are certain things that doesn't usually change, like how you can use encoders on your motors for accurate moving and autonomous. And then for this year, you can even use encoder values for the shooter mechanisms, which I will demonstrate at the end of this workshop. Also, even distance sensors might be useful for odometry as well, and getting some useful data for shooting, how far you can shoot. Other things you can do is that I know last year's control award winner used color sensors actually in autonomous, so they can stop right above the tape. So they detect the color of the tape or the color change, and then they stop their robot in autonomous, and then they can also recalibrate their encoder values by doing that. For this year, you also you can use USB cameras this year as well. That's now legal. You don't have to use the phone camera for object detection. And definitely object detection is really useful for this year because so for autonomous, you need to detect how many stacks of the rings are there. So for detecting that, definitely vision would be the best way to go for that. So these are definitely the things that we can do for this year. And yep, I would pass it on to Ben. Would you like to screen share, or would it be fine if I continue screen sharing? Oh, I think you're muted right now.
Thank you. Okay, I would like to screen share if that's possible. There we go. Okay, everyone should see Blocks 101. Are we good? Nope. Okay, I'm going to try. Okay, let me just a minute. Let me find out why that wasn't. Where's my. Okay, I'm going to try that screen share again. Actually, before I do that. Okay. Okay, can you see the blocks 101? Okay. All right, good. All right. Yeah, so I coach students, beginning programmers, becoming intermediate programmers, and they're all on Chromebooks. So just tapping into what Toyo was saying, very different scenario than what he was describing. And so blocks programming works really well. But I think there's value in what I'm going to show you to everyone. Now, in terms of, well, for beginners and intermediates, it's because it's blocks. You can really spend most of your time just developing the logic, the algorithms. You're not getting messed up with syntax errors, and there's a lot being done. Like, for example, all the variables are being typed for you. There's a lot of stuff going on in the background just to make sure that things are going to work. And so, yeah, that also makes it pretty quick coding for everyone. So one of the things about blocks programming is I ask that all the team members know a little bit of coding. And that would be true, for example, let's say you're installing a servo and you need to calibrate the horn so that the grip is just right, you know. Well, with a few moments with blocks programming, you can be calibrating that horn. Without having to go grab your programmer and build some Java code. So yeah, so there's a lot of value, I think, for everyone. Okay, so with that said, this is a blocks program, and there's the initialized blocks. Just a minute, let me. Okay, there we go. There's the initialized blocks at the top, everything until you get to call or await for start. And the drive base is the name you saved your op mode as. And so everything above is the initialize, everything below is the run. And this would be for a teleop program where the run blocks are being repeated as long as the op mode is active. So there's the telemetry blocks are telling the keeping the driver updated in terms of the status of the robot. There's really not a build with blocks, but the saving is manual. So just save early, save often. And every time you save, you're basically putting it on the program to run. In fact, with blocks programming, the programmers can be programming while the drivers are driving the robot. Not on the same program, obviously, I mean, on a different program. Well, actually, it can be on the same program. Programmers can be programming while the driver's driving on the same program. However, the updates the programmers made won't be in effect until the driver hits the stop button and then hits the play button again. Anyway, okay, so all these blocks, like oh, these are variable blocks down here. They're all grouped by function, and these are the functions here. There's a couple of blocks that are in funny places. Like, for example, you look over there, there's no motors. Well, it is, it's under actuators. One of the blocks that I try to get my students to use as much as possible is the commenting. Toya mentioned that. And that's under miscellaneous. Like, really? Okay. Telemetry is under utilities. That's another really important one, kind of buried underneath there. The sleep timer is under linear op modes. So there's a few little groupings or places that where the blocks are hidden away. But okay. And then here I'm using the comments, and that first block program I showed you is from the templates. There are a ton of templates built into blocks programming that are great for learning and get started and testing. But one of the first things I have my students do is create some variables and break the program up into functions. You know, the functions of a robot in the most general sense are to sense, think, and act. And you can see I did that with the commenting. And so the sensing would be just reading the gamepad. The thinking would be all your calculations for the example given there. It's just flipping the y-axis on the joysticks. And then the acting is sending the power and messaging the driver in terms of the status of the robot. So one of the first things I ask my students to do is, well, think about control. You don't want your motors going full power all the time. So this is kind of giving some power control, kind of speeds, like speeds on a bike. So for example, when they press the A button, they're going at half speed. So that gives them a lot of granular control on those joysticks. Now, back to what Toya said, in blocks programming, there is like naming variables. So you can see what I did here, a power left, power right, power band. So because variables are listed alphabetic order, I'm grouping all the power variables under, you know, as in the left motor, right motor, which speed it's going, all that kind of stuff. I've grouped it under the power grouping. So when I get a list of variables, all those variables are grouped together by alphabetic order. So as your programs grow, that becomes huge. I also use that strategy for naming the opcodes to begin with. I'll show you that a little bit later on. So here's a finished teleop with some speed control and a lot of commenting, just so you can follow the logic. This little arrow, I put it side by side. This is just one long program. I put it side by side so you could actually read what's going on. Right, so I already mentioned this, you know, like drive base speed, just really strategizing about how you name your op modes. Auto sprint, this would be the autonomous programs, auto square, that kind of thing. You can see that this is the desktop, the top screen for blocks programming. And you can see you can sort by op mode name. So you can see a list of drive base with a couple of different categories on that. There's no versioning in blocks. So, but what you can do is select and then copy the selected op mode. So you can manually version by saying, well, drive base 1.1, drive base 1.2. And then you can also sort by date modified. Yeah. I also, as you add, I tell my students, when you're going to add a new feature, make a copy of your working program, because typically things break before they work better, right? That's not our intent, but that's what ends up happening. This is an example of an autonomous code. And it's generally with autonomous, you can drop the repeat and just make, there's different kinds of autonomous programs. I won't jump into that, but very similar to your teleop program. Here under samples is where all your templates are. And at this, every year they add more templates. So there's now templates for different sensors, and yeah, there's over a dozen templates now. It's a great learning tool to make a quick way to check out sensors and things like that. Now, in terms of messaging the robot, another strategy is just get your robot to talk. And this is a great strategy for troubleshooting autonomous. So in this case, I'm using well, here's the autonomous program here on the left side. And here's the initialization where you set up the pitch and the speech rate and stuff like that. And then creating a function called speech and passing a global variable called speech text. And so this is the little function that gets the robot to talk. And then back to the actual run blocks here, speak with, and you just type in your text. This is a great way when you're designing your autonomous program. You might say, do a right. Your robot might say, okay, I'm going to do a right turn. And you can just see each chunk of your autonomous program working, and your robot's telling you which chunk it's on. You can also do this with text telemetry, but yeah, so blocks programming makes it really simple just to bang out a simple program to test your sensors and learn how your sensors are behaving in the field before you try to start integrating them into your big program. So for example, this autonomous program has got touch, color, timers, the voltage, a bunch of different stuff, but you can, and then this is a little trick. You know, there's only about 4 lines on a typical cell phone for your, on your driver station for telemetry. So a couple of strategies. One is to just pack that data in, and you can do it with the create text. You can see that I wanted to know the colors that the color sensor is detecting. So by doing a create text with, it goes on one line, it goes red equals in the value of red, blue equals in the value of blue, green equals in the value of green on one straight line. So you can really pack stuff in. Other ideas. Oh, in practice, sometimes I'll have the kids, students, excuse me, get out tablets, Android tablets, which will have dozens and dozens of telemetry lines. Of course, that's not allowed during competition, but as you're developing your autonomous code, it makes for much quicker work. Testing encoders. Yeah, encoders are, yeah, learning how encoders work is a bear for beginning programmers. So I just have them bang out a real simple test program, and the encoder reports to the driver exactly what the number of ticks are, and you can just mess with this. And once you get the encoders working, then you can say, okay, let's bring it into the into our big programs. Whoop, that was not meant to be there. All right. Functions. Yeah, functions allow you to segment your code. And so this is the autonomous program here. And you can see it's going forward 0.5 meter, left turn by 90 degrees, forward by 1 meter, and a left turn by 90 degrees. Very, very easy to follow that logic. Each one of those is a function, and you're passing variables. Here's one example of a function where it's distance meters is, yeah, distance meters is the global variable, and you're passing that, and on everything, the telemetry, the working with the encoders and all that is all in that function. If you did not use functions, you realize that like this chunk of code on the right-hand side would be repeated over and over and over again, and following the logic of your autonomous would be a struggle. I mean, you could do it, but testing servos. I mentioned earlier about getting a super simple servo test program that will actually report the position of the servo to the driver station. So if you're a builder, for example, and you're trying to get that horn just right, use this. And you can see what I'm doing here. I'm just using the gamepad. This would be teleop code, and I'm using 3 buttons. No, actually, using a bunch of buttons. I'm using all 4 buttons. So X would be a servo position of 0. B would be a servo position of 1, which is 180 degrees, or 200, depending on your servo, how it's configured. Some servos would be, some servos would be more than 180 degrees. And then your Y and A buttons is going to change the servo position by 0.05. So this is super, super helpful for builders. Okay. Yeah, our time, I really want to steer you towards these learning resources. There's from the firstinspires.org, that's our FTC main website, the resource library. There's a couple of blocks programming documents that will get you started. There's a block programming reference manual by Bruce Schaefer of Oregon Robotics. And this is a reference manual. So I'll have the students go there when they want to know, for example, the range of values for a servo. That kind of thing, a lot, or actually how the IMU works, the range of values for the IMU. There's a ton of information here. Don't read it like a novel, and it's not an instruction manual, it's a reference manual. For learning these videos, Bruce Schaefer, again, he's absolutely fabulous. These videos are like 5 minutes. He's broken them into like getting encoders working, or making your rotation sensor, or navigating with a rotation sensor. There's a ton of stuff. This is YouTube, so search for Bruce Schaefer and go to his playlist, Blocks Programming. Same thing with the First Tech Challenge channel. And they have a list of blocks tutorials. Half of them are actually done by Bruce Schaefer, and they've just copied them over. And then when we all get stuck with programming, we head over to the FTC forum. There's a lot of huge amount of information there. Best programming practices. Yes, I've already talked about some of this. Grouping by robot purpose, using functions. You can use local variables within functions. You can actually kind of pseudo multitask in blocks, and I'm not going to talk about that now. I did it on my own robot when I was learning blocks programming, which was about a year ago, but my teams haven't gotten there yet, so I'm gonna skip that for now. Yeah, sensors are slow, so keep them in their own forever loop. Oh, comments, document, and then use telemetry to keep the driver informed. Yep. More blocks tips. Oh yeah, so unlike with Java, you can build up libraries and that your programs can draw from. You have to manually do that in Chrome. So move your code chunks into functions. in blocks programming, have a couple of programs open in different tabs, and you can actually copy and paste functions from one tab to another. Now these don't update. So if you're in one block program and you update the function, you're going to have to manually go back to your other main blocks programs and just paste that function in. You can download your blocks programs and actually program on your laptop without your robot anywhere near. And then you can upload the programs when you get back to your robot. That's really pretty cool for like Chromebooks. You don't have to install Java. You don't have to install blocks. It all, yeah. They now have an export code as picture button. That's good for documenting your coding. And then actually, for example, your blocks programming connection is through Wi-Fi. And so on the programming computer, I typically add a second Wi-Fi dongle, a USB Wi-Fi. On this laptop that I'm presenting with, I'm actually connected to my programming, to my robot controller through Wi-Fi as I'm connected to internet through Wi-Fi, different Wi-Fis, 2 Wi-Fis. Let's see if I can, I'm gonna show you just a couple of things. That's pretty much the bulk of what I wanted to show you, but let's see if I can share. I'm gonna do a new share on my, where's Visor? Just a minute, I should have had Visor out. Visor's out. Oh, no. There's a program called Visor that allows you to put, I'm talking and working at the same time. There's, what happened to Visor? The Visor open again, okay. Somehow Visor went away. Oh, that's it. Got it. Sorry, I minimized my screen. Let's see if I can try this again. I'm going to try. There we go. There's my phone. Why did I want to show you this? Oh, yeah. Well, okay. You're being patient? Okay, I'll show you this. This is you can see what I've done with the names. So these concepts are basically all templates downloaded, followed along with the tutorials. These are autonomous programs. These are teleapp programs. These are programs for testing sensors. So you can see how I used the naming scheme. And then if you click on any of those, you can see there's the download offline blocks editor. There's the copy selected op mode. I think, yeah, I think I've come to a good breaking point. So I'm going to stop my share. If I can find my button. Where's my, shoot. There we go. Okay, thank you.
I'll start sharing my screen this time. Okay, so in the chat, I'll just post some additional resources this time for some Android Studio and or, well, Java programming, I would say, especially related to this year and some others. The first one link would be my team's GitHub. Just as long as you don't like copy everything off it, it's just like a nice reference to have if you would like to reference it again. And then Roadrunner, the second one that is. Roadrunner is like a software, or like it's a software that FTC team called ACME Robotics, they made the Roadrunner, and it basically allows you to draw a path in autonomous so that the robot can just follow the path. And then the third one would be like a nice video on shooting and kinematics in this year's game. I'll just warn you that if you don't really like math, I don't think you should watch that one because there's a lot of math that's involved. But it's really nice to understand like what's going on with the kinematics so you can have accurate shooting in this year's game. And then the fourth one is a video tutorial of detecting the starter stack. So this one is by wizards.exe, which they always make great videos and tutorials if you want to check them out. And so they use like Android phones, and even and you can also use like the external USB cameras and you can just follow their instructions so that you can detect the starter stack in autonomous. So these are some additional resources. Okay, so I'll just quickly re-screen share because that one was only my screen share on this one. And then actually, let me just switch up some order. I'll just show you guys what I will start demonstrating on. So hopefully you can see this mini contract, like a shooter thing that I just created. And then I'll just demonstrate some shooting with this polyop. Hopefully that works. All right. I'll stop it right now. So basically what's going to happen is that when I press it, it's just going to move, and I will get some values onto my telemetry. And this is probably where Ben's using the Android tablets would work better because this is a really tiny phone, so you can't have too much data. But if I press the start button, and hopefully you can see all these values. And then what I set the code to do is that it's going to make the speed close to 5. It might be harder to hear because of the noise, but I set the speed of these motors, the linear velocity, to be close to 5 meters per second. So you can use these kinematic equations, for example, and plug that number in so you can have accurate shooting every single time, and it goes into the goal. So I'll just demonstrate some shooting right now. I have this tape over here, and I have this mini thing that can feed it through. So if I can just put this guy right here. And basically you can just do the same thing with, the rings. That was just a Scotch tape, but it works a similar way. So I'll just quickly show you the code for that one, so you guys can do that with your robot as well. Okay. If Android Studio works. Okay, there we go. So here's kind of what I have for that piece of code. So in the beginning, I have a lot of variables that over here. These are just basically the values that you need for these calculations. And really how to get them is really just, okay, let's go to Google and then Google them all. So the max RPM of your motor, for this year's game, I would probably suggest that you get a 1620 about RPM so that it shoots well consistently. So that would be like a Neburst 3.7 or a Yellow Jacket 3.7 motor. And then I put the wheel diameter so I can get the linear velocity of the motor. And you can just, take the diameter in inches and then divide that by 39.37. That's just converting it to meters. And then, d pi, that's circumference. So that's all the calculations. And basically that's calculating all the different values that you need for the calculations. And one thing that's always useful in every year are PIDs. These are some like a little bit advanced topics, but what PIDs do is that you can make a certain value. And in this case, let's say for our shooter case, that will be the goal speed. So in that example, we wanted the speed of the wheel to be 5 meters per second. So we want the motor speed to be close to 5 meters per second. So when you want something like that, some value in real life to be close to a certain value, you can use something called PID. And I wouldn't go too much in depth of this because that will be kind of outside of the scope and it's an advanced topic. But simply said, just this first value is going to make how much you're correcting each time, how much you're correcting the motor speed. The second value would be after a certain amount of time, if it's taking too much time to reach a certain value, it's going to add more speed increasingly. And the third value would be how much it's dampening. So how much it's, so the value oscillates, but with the increased dampening value, you can make the oscillation a little bit weaker. And then I have the constructors over here, setting up the motors like usual. In this example, I'm not using encoder. I'm having the mode run without encoder, but I am using encoders later, which you will see. And here is the function that I'm using to shoot the motor or shoot the disk, I guess, and then turn the motors. So because I don't have a joystick right now, I can't really use the button. So I just set this to true for now. But basically what's going to happen is that when you press the button, it's going to shoot. Here I set the goal speed in meters per second. So in our case, it was 5. And here is the variable that's getting the difference in time since the last time that the loop ran. And I wouldn't get into too much in depth of this, but when the time is too quick, the encoder values don't change at all. So what you want to do is have a certain amount of time interval. In my case, it was 0.02. So after each 0.02 seconds, this piece of code is going to run. And this is the calculation portion of it. So now you're getting the position difference, the left shooter encoder position minus the last left shooter encoder position. And the same thing with the right encoder. And what you can do with this is that you can divide the time difference that you got here. Or actually, you can divide the position difference that you got here by the time difference that you got over here. So now, the position divided by time, that's going to be your speed, the rate of change. So that's what I'm calculating over here. And then I'm just converting it by multiplying by revolutions per ticks. And all of this calculation, remember, I had it over here. And here is where I am using the PID values. So what setPoint does is what you're going to include in the parentheses is going to be your goal value. So your goal value is 5 meters per second. So that's why I put goal speed MPS. Oops, that was too far. And your input range is what you want to make, what value you want to make the value close to the goal speed value. So that would be, or actually, I'm sorry, the input range would be the range of the value that you want to change. So the speed of your motor is going to be from between 0 and the maximum meters per second. So that's why I have the input range as 0 to maximum meters per second for both of them. The output range, the function set power for the motors, they can only get the power, they can only get the range -1 to 1. But since we don't want the motors to go backwards and just shoot right back into the robot, you set the out range to 0 to 1. And then you enable the PID. And here are the values that you're going to put. The speed, the left motor speed wants to be close to the goal speed meters per second. The right motor speed wants to be close to the goal speed meters per second. So these are going to be your power left and power R. And because you set the output range to 0 and 1, this code is going to calculate for you how much the shooter has to correct to attain the value of 5 meters per second. And again, like how Ben said, telemetry is really important because you want the value, you want the drivers and the builders to get the values, and you also want to get the values if you're a programmer to debug your code. So here I'm just adding the data, time difference, time diff, position L difference, and all these different variables. And yeah, that was my code for shooting accurately. And what you can do with this value is that you can even put this value into some calculations so that since you know the height of the goal and you know the distance, if you have a distance sensor or if you have a camera, you can know the distance between the robot and the goal. And now you can use this meters per second value to calculate how far, if you shoot a ring, how far it's going to go. And that's how you can facilitate the driver shooting. Rather than the driver going to a certain position every single time, you can, with programming, you can automatically like calculate how fast the motor should move. And then one thing I would like to add some tips and tricks is that when I was debugging this, I had a lot of problems while making this piece of code, like how programming never works the first try. So what you can do with comments, with comments, you can always, like the name suggests, you can put comments like, okay, this piece of code calculates the speed in meters per second. What you can also do is by using multi-line comments, you can type in slash asterisk, then asterisk slash. And then what you can do is that you can make this piece of code not run. So now you can isolate your problem of your code. So is it like, if you want to know which part of your code is causing trouble, you can be like, oh, maybe if I comment out this piece of code, and then maybe my code is going to work. And if it does work, and then you're now thinking, okay, now what part of this code doesn't work? And then you're just trying to isolate the problem, slowly making the space between the comments really small. And then it's like, oh, right, this is what was wrong with the code. And again, when you want to check out the code for that shooting, you can just check out my the GitHub for FTC team 16660 that I sent previously. And you can also find the PID controller code in the GitHub as well. So that was my demonstration on accurate shooting.
Awesome. Great timing as well, both of you. I guess we have a few minutes for audience questions if anyone has questions for them. I guess if no one else has a question, I can jump in with a question. So I know that there's one of the big things is how you tune the PID, and you talked a little bit about looking up the values. Do you ever like modify the values yourself, or do you always find that what's online is working?
It definitely differs between what things you are using. You can't just find the right values online or anything like that. If I could screen share again, I can show you that for last year's code, if it loads. Okay, hardware, drive, holonomic drive. So this is what we use for moving our robot, for usually even both teleop and autonomous, it's both in here. So I think it's at the top. Oh, I set it all to 0, so I have to, sorry, it's taking a while. I go to hardware over here. There you go. So depending on what things we are doing. So for driving, you don't really need an eye because it wouldn't, unless there's like crazy amount of friction or anything like that. You don't want to overcorrect every single time because that would be a pretty bad driving experience. So that's why there is no I value or D value. But on the other hand, for turning, let's say in autonomous, when you want to turn, if the robot doesn't turn all the way, let's say to 90 degrees, and it never does because the friction value is too high, and then you want the value to increase slowly, like your motor speed to increase slowly, depending on time, because then your robot's never going to turn 90 degrees. So that's why you have a little bit of an I value, but usually increasing this value too much is going to like overshoot so much. And one year we had like a robot, we tried testing it out and just started spinning around and around. So you never want to like have a too big value. And the D values are always hard to experiment with because they're really just a dampening factor, and usually P and I are sufficient. And sometimes you have to add D, but really it's just tuning and just messing around with the values and be like, okay, maybe try this value this time. And then it's like, okay, that oscillated too much. Maybe increase D or increase P or decrease P. There's definitely different documentations online. So for a better explanation, I would say I would go looking into in online.
Any other questions?
I've been in and out of the meeting tonight, so I'm not sure if you've already answered this, but when you guys were talking about the control award, did you talk about how many autonomous programs or variations of autonomous programs you usually have? Or is that a silly question to ask?
So how many autonomous programs we have for like, how many
different scenarios do you plan for? Or how do you plan for various scenarios based on like where your team's robots are placed, or, you know?
Well, I mean, you always want to have the most points for autonomous. So of course you try to include as much as possible, like as much points as possible into the autonomous, but at the same time, you also want to like make a program that you can coordinate with your teammates as well. So for last year, it was Skystone. There was 2 robots, and then one can go to like the left side and the other one can go to the right side. So we kind of set it so that maybe if the opponents, or not the opponents, if a teammate has a program, a good program to get all the Skystones onto the other side, maybe we can just bring the build plate first and go to the left and grab the build plate. And of course, we can always coordinate between matches or before matches, so to quickly add like delays and whatnot. So that is kind of my thought of doing autonomous programs. And if you want a discrete number, we had 8 different variations of autonomous last year.
Very nice. Yes, I do remember when I was coaching teams, that was kind of a going from rookie to the next step was figuring out that you needed to be prepared with variations of your autonomous programs. And 8. Nice. Okay, 8. Cool.
Awesome. Well, if that's all the questions, thank you guys for coming. And for those who have come to multiple, thanks for sticking around for all these. And yeah, I look forward to competing with you guys later this season. Have a good one.